Okay, next video, we're going to work with these guys a little bit. And so we have the problem twice. Again, I'm going to do it the way that you app users, you're going to see it. And please try not to use apps. They do not help you learn anything. And then the way I hope that you will do it. But just for emphasis here, that's cotangent 1/2 x plus 8 dx. And so I can let u equal the inside function. So u would be 1/2 x plus 8. That makes du 1/2 dx. Remember, we're just differentiating there. You differentiate the line above, end with dx, and then solve for dx. So dx will be 2 du. So then making my substitution, all of that's going to be u. dx is going to be replaced by 2 du, because that's what we calculated dx to be. And so that 2 can come all the way out. And we have cotangent u du. Step 5, still unnecessary. We will eventually get to that, I promise, but those are the harder problems that are going to be at the very end. Step 5, unnecessary. Have one variable. So then you just memorize that the integral of cotangent is the natural log of the absolute value of sine, u in this case, and then back to the original variable, 2 times the natural log of the absolute value of sine of 1/2 x plus 8 plus c. And then we haven't said it for a while, but you could check that by differentiation, and it would check back. And so absolutely, you can do it with a u substitution. But again, I want you to become a little more sophisticated. When your substitution is really just a linear thing, mx plus b, in this case 1/2 x plus 8, we've talked repeatedly about those linear things that you could just use what was on this previous page, right there, that the effect of that slope is that we're just going to divide by it. So using that the integral of cotangent, the integral of cotangent mx is just 1/m, the natural log of the absolute value of sine mx. I can do the same thing here. That using that m equals 1/2, lickety split, 1/m, so 1/1/2, 2. The natural log of the absolute value of sine, 1/2 x plus 8, plus c. The point being that yes, you can, and if you need, I don't want to scare anybody off from doing linear u substitutions. If this is what makes sense to you, and this is what guarantees you get the answer every single time, then by God, do that. But if you are truly understanding that when my arguments are linear, mx plus b, the effect of that slope when I integrate is going to be divide by it. And so when I divide by 1/2, I get 2, and then the rest of the problem, the integral of cotangent is the natural log of sine. Angles don't change. And so if you can remember that when I'm integrating, the effect of those linear arguments and the slope is just divide by it, that'll save you a little bit of time. But if you need to do a u substitution, understand it, then by God, do the u substitution so you can understand it. Okay, so there's that one. Okay, next problem. So let's start by doing it wrong. So we did a couple problems where u equal the denominator worked. So let's try u equal the denominator. See what happens. Because you will make bad choices. So if I let u equal the denominator, u is going to be 16 plus 25x squared, which will make du 50x dx. That x. There is no x in the problem. Not working. And so you just give up on it. Now, yes, sometimes there's ways to fudge it, but this is Calculus 1. Things are pretty much supposed to go okay. They're not supposed to be really horribly difficult. Now, every once in a while we'll do a horribly difficult problem, but in general, you don't have that variable part, you're going to try something else. And so, oh my God, I don't remember anything, so let's go back to this list right here. U equals something to create the form 1 over a squared plus u squared du, which integrates to tan inverse. When I see this constant over another constant, doesn't matter, plus square, and that's what I kind of have there, some number on the top. Then I have another number and a square. Think inverse tangent. And try to create one over a squared plus u squared du, which integrates to 1 over a tan inverse u over a plus c. So when I see constant, and these are different constants, I just don't have a notation to write constant, they could be the same or different, doesn't really matter, but these could be different constants. But constant over constant plus square, which is the form I have here, a constant over something squared. Now it's 25x squared, but still squared. Think tan inverse, and you're going to try to create 1 over a squared plus u squared du, because that I know how to integrate. And that's one of the things about substitutions, is you're trying to make known forms. So let's try to do that. So that 3 I can certainly factor out. I'm going to go down next line. So that 3 I can certainly factor out. Then 16 I could write as 4 squared. And the 25x squared I could write as 5x quantity squared. And so I'm starting to achieve that form. So the 3 I just factored out. So I have the 1. I have an a squared, 4 squared. Don't have quite the u squared, but I can make the u squared very easily. I'll let u equal 5x. Because I want a squared plus u squared. I got the a squared. I now want u squared. I don't want to see 5x squared. I want to see u squared. So I'm going to let u equal 5x, which will make du 5 dx, and makes dx du over 5. And so that's u. Dx can be replaced du over 5. That 5 can come all the way out to the front with the u. And I have 1 over 4 squared plus u squared du, which that is going to integrate with, in this case, a equal 4. That's going to give me 3/5 times 1/4 tan inverse u over 4 plus c. for a final answer of 3/20 tan inverse. U was equal to 5x, so 5x over 4 plus c. And in my opinion, that is by far the easiest way to do this sort of problem. For those of you that do app work, they do funky factoring, which is harder. This is easier. But the real point to this one, starting to recognize this form here. Constant over another constant. These do not have to be the same number here. But constant over constant plus square. That if you have that form, you're going to try to create 1 over a squared plus u squared du, which is going to integrate to tan inverse. Okay, so much for that one. Okay, next problem. So I'll kind of foreshadow here, and then we'll end the video and go on to the next problem. So we did 1 over a squared plus u squared. We learned about that, and that went to tan inverse. If we look above here, the integral of 1 over the square root of a squared minus u squared du, that's going to be sine inverse u over a plus c. So there's another form that we're going to have to learn to recognize when we see it. And we'll see that on the next video.